Let's go ahead and talk about the history of the atom. So, first off, we have a person named Democritus. He came up with the idea of atomos, which eventually became the word for atom. Now, what he did was that he thought of the atom through a thought experiment. And the thought experiment that he came up with was that if you had an object and cut it in half, and then taking one of those pieces cut in half again, repeating that process, would you eventually come across a piece that was so small you could no longer cut it in half? And what he thought was that eventually there has to be a stopping point. And so what he thought the atom was going to be a solid, homogeneous sphere that was made up of the original material. So if we had a brick cut in half and go all the way down to the atom itself was essentially the essence of the brick. After him came Dalton, and he came up with 5 different ideas that he thought that all atoms had to follow. His first was that all matter is composed of very small particles called atoms. Atoms of an element are exactly the same. Atoms cannot be created or destroyed. Atoms combine in whole number ratios. And in reactions, atoms are only rearranged. They are not created or destroyed. Now, through our development of atomic theory, some of these are still accurate, but others need to be revised or are completely wrong. So, for example, number 2, that all atoms of an element are exactly the same, this is no longer true. And we know this is no longer true because we have things called isotopes and ions. So, isotopes are going to be atoms of the same element, but they have a different mass to them. And then ions are going to be atoms of the same element, but they may have a different charge to them. And then number 3 is going to be that atoms cannot be created or destroyed. Now, we know in everything that this is no longer true because of the use of nuclear processes. So we are able to create new atoms, we are able to destroy them and break them down. So number 3 is no longer true due to nuclear reactions. After Dalton came J.J. Thomson, and he discovered the electron. Now, what he did was that he shot a cathode ray between magnets and observed the beam always bent towards the positive side. Now, what this meant was that because opposites attract, the beam must be made up of negative particles, and he called those negative particles electrons. And he came up with the idea of the plum pudding model. And what essentially this looks like is going to be a blueberry muffin, in which case the muffin itself is going to be the atom, and the blueberries are going to be the electrons. And those electrons, those blueberries, are just kind of spread randomly throughout the muffin. And he thought the atom was essentially the same idea. We also have Rutherford, and he discovered the nucleus of the atom. He discovered that the atom is mostly empty space as well. Now, his experiment that he did was that he shot positively charged radiation at gold foil. Now, most of the radiation passed through, but some of the radiation bounced off. And the only explanation for some of the radiation bouncing off was that there was a small positive center in the atom with the electrons just kind of scattered around it. Now, what and everything this really looks like, because his experiment was pretty impressive for the time. And so if we had our nucleus, we had our rings around it, we had our random electrons kind of scattered throughout. Now, what he did was that he shot these really high energy, like radiation particles, at this gold foil. Now, most of the radiation was able to pass straight through. But every so often, one of these radiation would hit the nucleus and then it would bounce off. And Rutherford came up with the only plausible explanation being that there is a really dense positive center inside of the atom. After Rutherford came Bohr, and he discovered that electrons are arranged in orbits or energy levels around the nucleus. And how he did this was that he used a flame test and observed um, the light energy that was released from those moving electrons. So, whenever we heat up an element, and whenever that energy gets released, it gets released as light. And that light and everything is very specific to certain energies. Now, through all of this, he came up with the planetary model, and so he assumed that the electrons orbit the nucleus in stable areas, very similar to how the planets will orbit the sun. So the sun would be the nucleus, and the planets would be the electrons orbiting around it. The Bohr model is probably the most famous model out of all of them, just because we see it the most often. All right, and then our most up to date is going to be the Heisenberg model. So he discovered that electron orbits are not predictable, and he named this the Heisenberg uncertainty principle. And essentially, what it states is that you can never know the exact position and velocity of a particle at the same time. And so, what this eventually led to was the electron cloud model, in which case there are only general areas of probability where you are likely to find an electron. So, we moved away from the idea of specific orbits or rings around the atom, and we now only have areas of probability of where an electron may be found. And so, this really leads into the really interesting idea of like quantum mechanics and quantum entanglement, especially with those electrons happening. Now that we have an understanding of the history of the atom, let's go over the basics of the atom. So, first off, we have our different particles, the electrons, protons, and neutrons. So, the electrons are going to be located in the electron cloud. Their symbol is going to be an E with a negative sign. They're going to have a charge of a negative 1, and their mass is going to be less than 1 AMU. So, essentially, the electron's mass is so small that most of the time we considered it to be negligible, meaning that we don't really take it into consideration very often. Our next is going to be our protons. They are going to be found in the nucleus. Their symbol is going to be a P with a plus sign. They are going to have a positive 1 charge, and they have a mass of 1 AMU. We then have our neutrons, also located in the nucleus. Their symbol will be an N, their charge will be 0, and they have a mass of 1 AMU as well. Now, if we take a look at this, we should notice that the majority of the mass is coming from the nucleus inside of the atom. So the nucleus is going to be where all of the mass in the atom is really going to be located. Now, what's going to really hold the nucleus together is something called a strong nuclear force. And this is going to be one of the four fundamental forces of the universe that we know. So we have the strong nuclear force, we have the weak nuclear force, we have the gravitational force, and we have the electromagnetism force. All right, let's talk about isotopes. So, some quick information about these. So, we are going to need our atomic number, which is going to be the number of protons. We have the mass number, which is the total number of protons and neutrons in the nucleus of the atom. So, those protons plus neutrons will equal the mass number. Now, what an isotope is that they are atoms of the same element, so they have the same number of protons, but they have a different number of neutrons. So your isotopes are going to have a different mass number than other similar elements. Now we have our ions, which are going to be atoms of an element that have lost or gained electrons, and they are no longer considered to be neutral. So when we have a neutral atom, we assume that the protons and the electrons are the same. So something becomes an ion whenever it loses or gains an electron. Now, one way that we are able to show an isotope is through something called the nuclear symbol. Now, our nuclear symbol I'm going to use, for example, is going to be hydrogen. So we are going to have our symbol of our hydrogen. In the top left is going to be the mass number. So let's say for this hydrogen, the mass number is 3. Now, the bottom left is going to be the atomic number, or the number of protons. For hydrogen, that is going to be 1. So just to make sure, what we're going to have in the bottom left, this is going to be the atomic number, which is going to be the number of protons. In the top left, this is the mass number, which is going to be our number of protons plus our number of neutrons. And then we are going to have our symbol. And that is going to be the nuclear symbol for our isotope. Top left will be the mass number, bottom left, the atomic number, and then we are going to have our symbol. Now, what we also have is something called the hyphen notation, which is essentially a shortened version of the nuclear symbol that it assumes that we already know what the number of protons is in an element. So, for example, we'll take the hydrogen 3. So we are going to write out hydrogen. We'll have a dash, and then we will have the mass number. So we are still able to get the same information from this. So we are going to have the name of the element, and then the number is going to be our mass number. So again, that's our protons plus our neutrons. And the hyphen notation is just a little bit of a shortened version of the nuclear symbol, and it doesn't give us directly the number of protons. Now, big thing, if our element or atom is considered to be neutral, that means the number of protons equals the number of electrons. So if we take a look at a nuclear symbol, so if we have our hydrogen 3, so we can have the nuclear symbol. We're able to write it out as hydrogen 3. Now, from this information, we are able to figure out that the number of protons is 1. Our number of neutrons will be 2. So our number of neutrons, the reason that we know what this is because the mass number is 3, and that is going to be equal to our protons plus our neutrons. And we know that our number of protons is 1. And so all we need to do is find out the number of neutrons. So 1 plus 2 will get us our mass number of 3. And then our number of electrons will be the same as our number of protons, as long as the atom is considered to be neutral. So in this case, it will be considered neutral, so our number of electrons will be